Yeah, last class we saw the constraints. Suppose if we write a general constraint equation, constraint as a function of the coordinate of y1, y2, yn, comma z1, zn, comma t is some constant. Okay. This is the holonomic constraint. Now, when you have a virtual displacement, because we need to find out what type of virtual displacement you can give, because they must be consistent with the constraint relationship. If you give a virtual displacement, the same relation is going to become like this: delta x1 so on and so forth, comma y1 plus delta y1, comma z1 plus delta z1, and this is the key. At time is kept same. You don't give a virtual increment to time, because what we are saying is at the same time, if there is a varied position, what that constraint will look like. So the time is frozen and you give a virtual displacement. Now you can expand this by Taylor series and keep it as a first order term. It will become f of x1, comma y1, z1, comma t, plus you will have the summation I running from 1 to n delta f by delta xi plus delta f by delta yi plus delta zi delta zi, and only first order higher, because virtual is a very small displacement, so higher order terms we are neglecting. This is essentially C. Because even in the virtual displacement the constraint relation does not change. Now you see this term is same as the first term. This must be 0. So the virtual displacements must satisfy. So I will write that must satisfy the relation summation I running from 1 to n delta f by zi delta zi. So this is the relationship. Okay. Now I'll just show by a small example what that relation really means. Okay, it's a very simple example. I just want to show that so that you can have a understanding of what we mean by this relation. We'll take the very simple problem where we had the mass like a pendulum. This length is L and L is constant. So if you say this is my x and this is my z, any position for this mass, your constraint relation L square is right, because the length is constant. This is a constraint which is similar to f of x1 to xn, that C. Now, if you vary, okay, let us apply that, because our function is this, okay. This will be delta f over delta x, because there is only one variable. So you will have delta x into delta x plus f over delta z, this is 0, okay. Now substitute, this is our f, okay. If you substitute delta x by delta x, this will become 2x del x plus 2z del z equals 0, 2 cancel out. You now know I cannot give independently any virtual displacement. If I treat one of them as independent, these are dependent on that. So you may call it my delta z is minus x over z delta x, okay. What it really means is, suppose if you take this, okay, this particle, because this length is constrained, it can only move this way, it cannot go anywhere, which means this, okay, this is x displacement, this is z displacement, okay. This angle is theta, so this angle is theta, this angle is theta. You know theta is x by z, you can tan theta with a minus sign, because this negative comes. So you will find that relation essentially tells I can give a virtual displacement only along a direction which is perpendicular to the string. That's all. That is what this relationship tells you, because you know that this will be del x, this will be del z. They cannot be arbitrary, because you can give only along this. That is why x over z del x, that relation. So if you complete this triangle, you will know that if I give del x, what should be my del z. That's all. So essentially the constraint is embedded in this relationship, okay. Now this is the basis, because this is always, you must understand, when you give a virtual displacement, it must be consistent with the constraints, and that as a relation, virtual displacement must satisfy that equation, okay. Now let us go to the situation of a energy virtual work done. Let us take one particle, one ith particle, okay, ith mass or ith particle or anything, because we are going to have n particles. So you can say ith mass as ith particle, and the resultant force acting on that, resultant force acting on this ith particle, I call it Ri. Okay. If this is in equilibrium, if ith particle is in equilibrium, okay, then Ri is 0. Okay. So Ri automatically becomes 0. And the virtual work done in moving this particle, virtual work, I am writing virtual work, delta W will be Ri dot, this is the virtual work, and this is 0. Okay. But now you go and then look at, okay, how is my Ri, what are the contributions? Okay. Ri will have an external load, external force, and a constraint force. Because you can have, like the simple pendulum case, there can be a gravity which is external load, and then the tension, that is a constraint force. Okay. So you will have this Ri can be split into Fi, which is external, plus some another lowercase I, which is constraint force. This is external force. Okay. Now if I substitute this here, I will have del W as F I external dot delta Ri plus Fi dot delta R. Right? And you know that if it is in equilibrium, virtual work is 0, this must be 0, equilibrium, but you know that this term, constraint force, cannot do any work, because you can only have virtual displacement which must be consistent with the constraint. That means the virtual displacement has to be normal to the constraint force. Therefore, this will not do any work. So this term is 0. And what will come out as the virtual work principle now is delta W is Fi dot delta Ri equals 0. Fi is not 0, please understand. Whereas here resultant force Ri is 0, because the body is in equilibrium. Whereas here, please understand, Fi is not 0. What is 0 is the virtual work done by the external force. Now if you have several particles, okay, that is, we said that there are n particles. If you have n particles, you will have delta W, you just put the summation. Summation, same relationship holds. So you will have Fi dot delta Ri equals 0, I running from 1 to 2. This is my principle of virtual work. For static equilibrium. Okay. Now comes your I'll write it. This is the principle of Suppose we have a situation, now dynamics, we are going to dynamics. What happens in dynamics? The particle is acted on by, okay, we have the particle is acted on by, this is a dynamic situation, okay. So I am writing dynamics. You will have an external load, okay, Fy external, possibly if you want, I can use the word external also. It is not a constraint, okay, Fy, but most of the books will simply say Fy dot delta Ri is 0. Fy external plus you will have constraint force and the particle is moving. So you will have Mi, mass of that particle is Mi with Ri double dot. Double dot is second derivative with respect to time. This is mass times acceleration for the particle. Okay. Now you see, this is where the D'Alembert's principle comes. This equation is converted into similar to static equilibrium equation. In the sense you bring this term to the left hand side. Left hand side if you bring external Fy minus Mi 0. So now this particular term I am calling it as an inertia force, okay, and this is called this particular thing, transferring Mi Ri double dot to the left hand side and then calling it as a force, as though it is a additional force. This is called the D'Alembert's principle. Call it as a force. Now summation of all the forces equal to, this is what we said, Ri equal to 0 like a static equilibrium. So this principle is called the D'Alembert's principle. Okay. See, it looks very simple, but it's a very meaning in that. What I am doing is a dynamic situation, I am converting into an equivalent static situation by calling this term as an inertia force. Okay. And now I simply go and apply my principle of virtual work where summation of Ri dot delta Ri is 0. So I will have what? We had this, what we wrote for static situation. I running from 1 to all the particles. I will go and substitute this term there. You know that constraint forces will not do any work. Therefore, what is left is summation I running from 1 to n Fi external dot Ri minus Mi Ri double dot delta Ri is 0. Okay. Because Fy doesn't do any work. Okay. Now for this particular term can be replaced in this fashion. So what you do is, it is just a small algebra here, okay, and you can just replace this term. Consider, suppose if you consider d over dt of Ri dot delta Ri. I am just taking a derivative of this term. This is going to be okay, dt of, let me write it. I think it is better to write in a, sorry. This is first Ri double dot dot delta Ri, okay, then plus Ri dot dot of d over dt of delta Ri. Okay, please understand, here I am going to make the time derivative of the variation is same as variation of the time derivative. This is a, that is why the varied path is a small slight change. Okay, so that is important thing. You can have a different type of a situation where these two need not be same, but here I am making that assumption that this term I can write it as delta of r dot dr by dt. Okay, that is, this will be like this. I am writing it like this. That is why the varied, okay, so delta of velocity. So this term I am going to write it like this: Ri double dot dot delta Ri plus Ri dot dot of delta Ri dot. This is, you can write it as half delta of Ri dot Ri, which is nothing but Ri dot basically square, velocity square. Okay, this is the magnitude. Okay, you can take it as okay, I will leave it as it is, Ri dot square, velocity square. Now what you do is, you have this expression Ri double dot delta Ri. You have here Ri double dot delta Ri. So bring that term to the left hand side and write this itself as summation I running from 1 to n f I external dot delta Ri. Then I am going to subtract the term, that will be minus of mi. I will have two terms, please understand, half, sorry, dy dt of Ri dot dot delta Ri minus half delta Ri dot square. This is a scalar. Okay, all right, and this is equal to 0, because that is equal to 0. I am just replacing this term by this term. I take it to the left hand side and I am writing. Now if you look at the individual terms, okay, Fy external dot delta Ri, that is nothing but the virtual work done by the external forces, okay, on all the particles. So I can simply write delta W, virtual work done by external loads. Then you go here minus mi 1 over 2 ri dot. Ri dot is velocity, half m v square, velocity square, that is kinetic energy. So I have the variation of the kinetic energy, which this is a minus and minus, so that will become plus delta t. Okay. Then I can transfer this term to the right hand side. Okay. When I transfer it, I will have equals summation I running from 1 to n mi d over dt of ri dot delta ri. Okay. Now I erase everything so that we will discuss a little bit about this particular relationship. So you see, what we have done is the virtual work for dynamics or dynamical system, you can say, under dynamic conditions is converted into this form. Okay. Now in this form it's not useful immediately. So what is done is, this is where Hamilton's principle comes into picture, because dynamics is motion with respect to time. So what he said is, he took a integral of this quantity with respect to time. When you integral of this quantity with respect to time is, you put t1 to t2, and this also becomes t1 to t2, whereas t1 is the starting time, t2 is the final time. Okay. And then put a dt. Please understand, you have to put a dt because you are integrating. So you have to put a dt. Okay. So I am basically evaluating the scalar quantity. This is work done. Please understand, this is work. This is kinetic energy. So these are all scalar quantities. The integration of this, basically the scalar quantity over the time t1 to t2, and then I am taking variation of that. But what is that variation I am talking about? It is basically assuming that the particles or the system of particles, they move from system of, this is at time t1, this is at time t2, initial time, final time. The system goes along some particular path. Okay. If you have, at every time you will have some particular position, that is the, you call it configuration of the system at that particular time, which is basically described by your generalized coordinates. Because generalized coordinate constraints are there, you remove the constraint, you have the generalized coordinate of the system. Every time you have generalized coordinate. Okay. And then this system moves along some path. This path is, in nature it moves, and this is called actually true path or Newtonian path. Okay. This is what is happening. But if you have a varied path, that means some path which is different, that means time is frozen, the path can be, this is at the same time. I can have this path or I can have that path. Okay, that is why time frozen, but it is at a different position. That is why in the constraint equation, time is frozen. Virtual work, when you take, time is frozen. Now you say that why the system has to follow that particular path instead of this path. Okay, because among all possible, you have to go from one time to another time in the configuration space, the motion. It follows some path. That is what we call it a Newtonian path, because that follows Newton's law. F is equal to ma. Everything follows. You can write that evolution of the motion of the particle or the system itself. But here, if you have a slightly different path, any various possible paths are available. But then, what this says is, the variation of this quantity integrated from T1 to T2, okay, this is the extremum or minimum. That is what we will show them. What we have done is, the starting point is known, because there is no variation in the starting point. I have not put, and end point also is known. Okay, so there is no variation in the starting point. There is no variation in the end point. That is the key. In between, it can go several paths. Okay, among those various paths, the system chooses a particular path for which this becomes an extremum. That is what we will show. Now, what happens to the right hand term, right hand side, this term? Because we said that the variation at T1 and T2 is 0, because there is no variation in the path at T1 and T2. So what you do is, this integral, the right hand side becomes essentially summation I 1 to n mi, because this is dt, dt will go, differential of this, it will be Ri dot delta Ri at T1 and T2. Okay, delta Ri at T1 and T2 is 0. So this term, there is no variation at the starting point and the end point. Therefore, this term becomes 0, and your Hamilton, this is what Hamilton's principle is. Okay, Hamilton's principle. Okay, T1 to T2, variation of T plus variation of W dt is 0. This is my Hamilton's principle. Okay, now I can slightly modify this. That's all. Now you have obtained, but the beauty of this is purely a scalar quantity. We are not talking about vector field, because Newton's law is actually force and acceleration relationship. It is a vector quantity. This is scalar. Now you see the nature, the beauty is, this gives you exactly the same result as what Newton's law gives, because this principle is like, in a dynamical system, if a particle or system moves from one configuration, one time to another time moving, it chooses a particular path for which variation of kinetic energy and the external work done is 0. And this path turns out to be same as the Newton's path. Now you can write this, because delta W is the work done by the external forces. I can split it into two combinations, because I can have conservative force. Please note that I can have conservative force or non-conservative force. Okay, because you can say gravity conservative, because the definition for conservative is, what is the definition? The work done, well, it is independent of the path, and the work done only on the initial and final position. Okay, that is the conservative force. Non-conservative force, no, it is a function of path, like a friction. Friction is a function. Aerodynamic load, you cannot take it as a conservative thing. Okay, so conservative force, the work done in conservative force is independent of the path, and here the work done, you can write it as, is actually a change in the potential. So that in this case, this will be minus del V or del U. They write it, V is the potential. You may call it, we call it potential energy. Okay. For conservative force only we can write. For this, it will stay as it is. Non-conservative, it will be just, work done will be just as it is. You don't do any potential type. Okay, work done will be just simply delta W non-conservative. Now I am splitting the delta W itself into two parts, work done by conservative force, work done by non-conservative force. So I will put it as this, as delta U or delta V, sorry, delta V plus delta W non-conservative. Now I substitute here, then I will have my V. Usually this is written as extended Hamilton's principle. Okay, Hamilton's principle. Delta T minus V plus W non-conservative T2 delta T is 0. Okay. So this is my Hamilton's principle. Okay. Now you can, so you see this principle in the broader class of calculus of variation. So it falls into that, because this is like a function. Sorry, yeah. Oh, dt. So we may have, that is dt. Yeah, sorry. See this. Yeah, this is a function. Kinetic energy, potential energy, and work done by the non-conservative force. Now this is integrated from some between 2 points. Here it is time. Okay, and the variation of that is 0. So in normally, you know, maxima minima. If you are given a function, if you want to find out what is the maximum or minimum, what do? You take the first derivative, set it equal to 0, and then find the solve for what points it is 0, and then if you want maxima or minima, you go to the second derivative. That is for a one function. Here This is an integrated value. A function is integrated, okay, and each one is a function of it is a path. There are several paths. So these are functions of another function. Okay. So they call it functional. You call it functional. That means all these are functions of path. You are integrating over the two time limits. In which path if I go, I will get every path. You go along the various paths. Okay. And then you will find that the variation of this, first variation 0. This is why this is called extremum, they will say, because you don't say minimum or maximum, because you don't go and calculate the second derivative. That is why this falls under the principle of calculus of variations, or variational calculus, you can call it. Okay, because that is a very general mathematical premise. Now we can derive the Lagrange's equation from the Hamilton's principle, or we call it extended Hamilton. Extended is, otherwise what they will do is, if you NC is 0, then they will say this is RT plus W, that's it, generally. Okay, you split it into that, you write it like this. Now for a deformable structure, you know that kinetic energy you can get for any point, strain energy you can get, virtual work done by the external load. So get that, you will write the equation. But please understand, this is not going to give you solution. It will give you only the equation of motion. Okay, we will do in the next class how we apply this for our problem, how do we get the equations, etc. That we will do it as a example. Now let us do the Lagrange's equation. Okay. So the Lagrange's equation is we have holonomic constraints. Please note, we have only this. That means, what is my position vector of any particle? Ri. Position vector is now written in terms of generalized coordinates, because holonomic constraints are there. I am not going to put x1, x2, x3 because they are all the coordinates, but there are constraints. That means number of independent degrees of freedom, which are called the generalized coordinates. They are less because of the constraints. So I am going to call those independent coordinates, or independent, basically they are degrees of freedom. I am going to use the symbol Q1, Q1, Q2, Qn, comma T, where Qi, these are degrees of freedom. Okay, ith degree of freedom. That means there are n degrees of freedom, n DOF. So n DOF. This is the n degree of freedom system. Okay, independent coordinates you can call it. Independent, actually, that is what the configuration comes. Now I erase this part. You calculate the velocity. Velocity will be what? Time derivative with respect to time. Time derivative, basically. Derivative with respect to time. You will have summation I running from 1 to lowercase n Ri, no, I'll put it here, J, Qj, because J is this, into delta Qi by delta, sorry, delta Qj by delta T, which is actually Qj dot. Okay. Plus you will have all right. This is my velocity expression. Now I have to get the kinetic energy expression. So the kinetic energy will be T is, I am going to have a summation here of all the particles. That will be, you can take it I running from 1 to capital N, 1 to capital N, half Mi dRi by over dt, dot product of okay. Now if I substitute this here, please understand one thing. I am going to substitute in this. This will be like a square term. So I will have something like this. I can write it as half summation I running from 1 to capital N Mi, open a bracket, summation, I will have K running from 1 to lowercase n, summation S running from 1 to lowercase n, delta Ri over delta Qk, delta Ri over delta Qs, dot product with Qk dot Qs dot. This is one term. Then you will have, because I have to square it. Okay, what will happen? This whole thing square means this term square plus 2 into this term plus this term square. Okay, so I can write it as 2 delta Ri over delta T summation. I can use any symbol K running from 1 to n, delta Ri by delta Qk, Qk dot plus delta T dot. Okay. This is a long expression. Now why do we write this long expression is, we always say kinetic energy is a function of velocity. That means velocity is first derivative of time. But here you note that Ri are functions of generalized coordinates. Please understand, they are functions of generalized coordinate. Therefore, when I have this term delta Ri by delta Qk, these are functions of generalized coordinate. I also have a time derivative of generalized coordinate. You understand? Therefore, your kinetic energy expression, when you write it, it is a function of T is a function, or I'll write it T is a function of Q1 to Qn, comma Q1 dot to Qn dot, comma T. Please understand, kinetic energy is a function of generalized coordinate and also its time derivative. So that is why this is very important to understand, because normally we'll think kinetic energy means okay, it's only a function of velocity square. Yes, but then when you are writing it in generalized coordinate form, it will be a function of generalized coordinate as well as its time derivative. Okay, that is the reason why we write all this long expression for you to understand. Okay, now we don't need this long expression, we will erase that part. We directly go for the, because you know that potential energy is a function of position. That means generalized coordinate. That means q1, q2, q3, qn. Okay. So I'll write this part again. So my kinetic energy is a function of q1 to qn, comma q1 dot to qn dot, comma t, and this is a function of only qn position. Okay, right? Because that is what the potential energy. Potential energy is only a function of position. Now what you do is you have to go and substitute these expressions in the Hamilton's principle and integrate them independently. So we will do step by step, one after the other. If you take the first term, because the extended Hamilton's principle is delta of T1, T2, T minus V plus NC dt 0. So I have to get first term, then the second term, then the last term, that variation. So what we will do is we will take the first term now, and that is, we know that delta T, because it is a function of qk q dot k. So I can write it as summation k running from 1 to n delta T by delta qk dot plus and then you have to integrate. Integrate means integral delta T dt T1 to T2. I am going to put this. This will be integral. You can have the summation inside or outside, doesn't matter. 1 to n T1 to T2 delta T over delta qk dot dt. I am writing it in two terms, plus integral T1 to T2, again summation, k, this is k running from 1 to n, again delta T over delta qk dt. Okay. Now what you do is this first integral, because this is delta by delta qk dot dt. Okay, this term you can write it as d by dt of delta qk. Okay, d by dt of delta qk, and then you can use the integral the u dv kind of a expression, u dv, and then integrate by parts. When you integrate parts, you will get this, that is delta T over delta Qk dot, because your summation is still there, delta Qk T1 to T2 minus, because this k is there, 1 to n, minus integral T1 to T2, you will have still the summation k running from 1 to n. Since this is integrated by parts, it will become d over dt of delta T over delta Qk dot delta Qk dt plus this term will remain as it is. The summation k running from 1 to n delta T over delta Qk dt. Okay. Now what you have done is, you say that, oh, this is delta Qk T1 to T2, because there is no variation in the initial and final time in the configuration. Therefore, this term goes to 0, right? And so what I have done is, I have taken this first term in this delta T dt, I have written it in that form. All right. Now we can write the, and this itself maybe will come here. Now variation in potential energy, that is delta V, because we said that potential is only a function of the position. So you will have, this will be summation again k running from 1 to n delta V over delta Qk. Okay. And then we need to know delta WNC. Okay. Delta WNC, that is the virtual work done by the non-conservative forces. You know that non-conservative forces, we have written it as, you may have say some P non-conservative forces. I am going to call that non-conservative force as, sorry, Fj, okay, Fj. Now drj, I have not this d, I am sorry about that, this is the delta rj. Okay. This I have to write it in terms of generalized coordinates, which will be delta rj will be delta rj over delta q1 so on plus delta rj over delta qn delta, sorry, I have to put a delta q1 here and delta qn here. Okay. What you do is, you take it, put it back here, and then collect the terms. Maybe I erase this part here, so that your delta WNC is going to become j running from 1 to p. You will have Fj dot, every term will be added. Okay. Now that will be delta r j by delta q1 delta q1 plus so on, plus you will have fj dot delta r q n. Okay. That means you have these n terms are there. Okay. I can write this as in a modified form. I will write it as summation k running from 1 to n q k n c delta q k. Okay. Because I am summing now with delta q rather than in the j. Now what is this factor? This is the generalized force. This is the generalized virtual displacement of the generalized coordinate. So qknc will be, I can write it here, qknc is summation j running from 1 to p fj dot delta r j over delta q k. Okay, this is my generalized force, non-conservative force. So essentially what I have to do is, I have to, because this is my equation, Hamilton's principle. So I have delta t minus delta v plus delta wnc. I have to add then this term and then this term. And I have dt. In every term you will see delta qk, delta qk, delta qk, delta qk, and dt is common. So you can write it as one general expression, one long one. I'll write that part so that that becomes a simple, because this is the final variation of T1 to T2, T minus V plus is minus K running from 1 to n, because I am taking minus, because delta T there is a minus sign. Okay, that's why I have taken that minus sign out. I will have this integral T1 to T2. I am opening a bracket. I will write d over dt of delta T over delta Q K dot. And then the second term minus delta T over delta Q K. Then I have to add the potential plus delta V over delta, because this minus sign is going to become a plus sign, because I have taken a minus outside, delta Qk. And then that NC term, NC, this will be a minus sign, it will come because minus is out. So I will write this as minus Qk NC delta Qk dt, this is 0. Okay. Now you say that since my Qk's are generalized coordinate, each one is independent. So I can vary that arbitrarily. That means integrand must be 0. and that is my Lagrange's equation. So Lagrange's equation is d over dt delta t by delta qk dot minus delta t by delta qk plus delta v by delta qk equals q k n c and k running from 1 to n. Please understand, you have n equations because k is n. Now this is one form of, this is actually you can use it as it is, there is absolutely no problem, but sometimes you define t minus v as Lagrangian. Okay. I erase this section because Lagrangian is defined as Lagrangian. You can say L is t minus v. Okay. Then what will happen? This term is delta by delta qk, delta by delta qk. So you can write it as minus of t minus v. T minus v is L. But here you know that potential is independent of the velocity term. Velocity means the time derivative term. Therefore, even if you add here, it doesn't matter. So what they will write is d over dt delta L over delta qk dot minus qk. This is the Lagrange's equation. Please note you have k running from 1 to n. These are the Lagrange's equation. And L is t minus v. Now you know even the Hamilton's principle, I am just giving you, Hamilton's principle was written as delta of integral if there are no non-conservative force. Then what will happen? No non-conservative mode, no non-conservative force, and this is Lagrangian. Okay, so it can be written as delta L dt t1 to dt this is called the principle of least action. Okay, they call it. All are variational calculus. If you see math, if you study the variational calculus, they will write for general function. Okay, here we are only writing kinetic energy and potential energy and some external non-conservative force. We split everything into energy expression. Whereas variational calculus, they will just write some f function, and then they say there are several interesting problems in math. I will not get into that. Now we have learned two things: Lagrange's equation, Hamilton's principle. What we will do next class is how do we use these to develop our equation of motion. Please understand, these equations will not give you the result, solution will not be given, they will give only the equation of motion. Okay, so don't think that because Lagrange equation, if I derive, I have the solution. No, solution you have to solve later. That is why in the aeroelastic problem, first you get the equation, then you look at how do I get the solution. Okay, so these are the two steps. We have the structural problems, but linked with, because here I have developed the equations with the particles and like a dynamic. What happens to a deformable structure? You can develop the same thing, please understand, but that you have to go for deformable bodies, but you will get identical Hamilton's principle and Lagrange's equations are same. So whether it is for a deformable body or for a rigid body, doesn't matter. You can use the same thing. Only thing is the formulation, how you develop it to this form. Here I use rigid body dynamics. You can also have, otherwise it is like a repetition of the same formulation starting from deformable body, you go here rigid body. Because anyway D'Alembert's principle is used. Okay. In the deformable body you use the Cauchy boundary condition and equilibrium equations in terms of stresses, and finally you will get the same formulation. Okay, there you write, instead of potential you write strain energy. Okay, that is why derivation and the formulation is same. Lagrange's equations, Hamilton's principle, and these are extensively used in developing the equation of motion for aeroelastic.